Now, we've already looked at taking single measurements and what its uncertainty would be. As a reminder, your uncertainty is the most precise digit of that measurement because it could be a little bit higher, it could be a little bit lower. You are somewhat estimating, or if it's a digital device, the digital device has a cutoff in there. So for analog, your uncertainty is half of the smallest tick, and for digital, it's just the last, whatever the last decimal place is there. That's the most precise digit of those instruments. Now, what about, though, whenever we take multiple measurements of the same thing? We're trying to do a repetition, if you will, to try to reduce error, because whenever we take a measurement multiple times and then average it, we do the exact same thing time after time after time, generally at least 5, it's going to reduce the random error, because sometimes it's a little high, sometimes it's a little low, because, quite frankly, our lives are not perfect. So let's say here we have the first couple of columns of a raw data table with times, right? I got these 5 times that I took. My stopwatch goes down here to 0.01 seconds, a digital device. So I record those uncertainties in the header. Each of these right here, 0.01 for all 5 trials, because it's just the uncertainty of that measurement. And so that would be the uncertainty of each individual one. I'm going to maybe blow up this little raw data table. You might recognize this slide from a different video here, just a little bit to where we can see. And so you can see we would have 5 trials over here, leading to an eventual average over this way, right? Right over here. And in each one we have the header of our uncertainty for entire one. So we're just using these couple of rows right now in a raw data table as an example. So I go ahead and I take my average here of all my 5 times, 1.65, which actually turned out to be exactly that. But of note, whenever you're taking an average of a bunch of measurements, make sure that your average reports the exact same number of decimals as as the measurements themselves, because your average should reflect the same precision as the instrument that you use to measure it. The instrument here, my stopwatch, went down here to the hundredths place. 0.01 would have been the smallest one, so notice I have 2 numbers after the decimal. So I would want to make sure that I average my times to also have 2 numbers after the decimal. That way it has the exact same precision as the actual measurements that I took. Now, what about my error or uncertainty here with this average? Well, you actually end up having a choice. It could be the uncertainty found in the measuring instrument, or the stopwatch, in this case 0.01. Or, if it's worse, which I'm going to go ahead and tell you 99 times out of 100 it is worse, your uncertainty should reflect the spread here of your actual data. So look here at the number line. I actually plotted out kind of on just a linear number line the spread of our data. It looks like we have an average here of 1.65, which happens to be one of our data points. That wouldn't always be the case. Maybe I'll put another dot right here to try to indicate that's where our average is too. And then we actually spread out from there, because it turns out here that our average, it looks like, could possibly, or our error bars could possibly run to the left and to the right a certain amount. Now, one of the ways that you can deal with this is you could run a bunch of statistical analysis, or a way that is acceptable right now for us in high school and generally freshman, sophomore year in college as well, is that you can take the range of the data, how far to the left, how far to the right it goes, or just subtract the highest minus the lowest, divide by 2, and let that be your uncertainty. All right, so whenever I actually do that, the range cut in half, trying to show that this average could venture all the way up to the 1.74 or come all the way down to the 1.56 number there, that there's an actual range of my data here, so the average could be slid somewhere in there depending upon measurements, right? Whenever I cut my range in half, I came out with 0.09 seconds would be my uncertainty. Now notice, this is larger than the actual uncertainty of the measuring device, so I'm going to put that in now for my average time. So I simply add it into that individual times box, just right there at the end of it. The only reason that we ever absorb anything into the header is to make life easier, because this uncertainty for the stopwatch, 0.01, would have been the uncertainty for all the times in that column there, so we can absorb it up. On the other hand, the average time uncertainties are going to be different, so I actually need to, because the range is going to be different for all different trials, so I actually need to put it into that average time box, just like as you might see here. Sorry for it being a little see-through and kind of odd there. Notice that here you actually have different ranges of times, so whenever you actually come out for each one of these, you'll notice that in the previous video and somewhat small over here, that you end up having different uncertainties for each one, for each trial, or for each, excuse me, different independent variable, thus leading to different uncertainties. So I can absorb that into the header. I actually put it on the actual average times. One final note that I actually need to make here, very important, all errors and uncertainties should be reported to the same number of decimals as their measurement, and it can include up to 2 possible numbers here. I should say not 0 numbers. So for example, here I came out perfect, right, with 0.09. It goes to the exact same number of decimals. It goes down to the hundredths place. My error or my uncertainty goes down to the hundredths place, and it only includes one non-zero digit there. If this had said 0.095 down here, another number afterwards, I actually would have had to round this because the measurement only goes down to the hundredths place. So if this had been 0.095, I would have had to round that. The 5 would have rounded the 9 up, the 9 would have bumped. This would have become 0.10 there for my uncertainty. But once again, I have to have the same number of decimals here in my uncertainty as I have in my actual measurement. To summarize, we end up taking measurements multiple times to reduce random error. The uncertainty of a single measurement is just from the device itself. But whenever we take an average, a lot of times the uncertainty from the average or the spread of the data will be greater than the uncertainty found specifically in the device. The data generally will be a little bit more spread out. So what you do is you cut the range in half. It's a pretty good idea of how much the average could vary. It will work for us for now. You add that in to that individual box. You can't absorb it to the header because each trial in your raw data table will more than likely be different. Make sure that you round your uncertainty such that it has the exact same number of decimal places as your measurement.